Hi Level 3s. Next we're going to look at angular momentum. So just going back to what is linear momentum. Remember that an object has linear momentum in a straight line as long as it has a certain velocity and by virtue of the fact that it has mass. Momentum is the mass times the velocity of a body. So similarly, angular momentum also depends on angular velocity and the angular equivalent of mass, which is rotational inertia. And so we use this symbol L, capital L, and it is equal to the rotational inertia times by the angular velocity, and it's measured in kilogram meters squared per second. And this comes from, if you work out inertia, which is kilogram meters squared, times radians per second to the -1, but we ignore the radians because it's a ratio, and so we just ignore that when we write the final unit. So next we look at conservation of angular momentum. So provided that there are no external forces acting, rather external torques acting, the total angular momentum of a system will remain the same. In other words, before or after a collision, for example, as long as you've got no external torques acting, then the momentum is equivalent. And you can look at the example on page 142 in your text. An example might be given of a skater spinning around in a circle, and when she draws her arms in, the center of mass becomes more concentrated, closer to the center around which she's spinning, which means her rotational inertia will decrease, and therefore she will need to spin faster to maintain the same angular momentum, again assuming there are no external forces acting. Another application of the conservation of angular momentum is a helicopter. So you obviously know that a helicopter has a large rotor that spins above the body of the helicopter, but because of the conservation of angular momentum, the actual body of the helicopter will want to tend to spin in the opposite direction to that rotor to provide that equal but opposite angular momentum. And so what happens is that on the back of the helicopter there is a small tail rotor that provides the external torque, and you can see here's the small tail rotor providing that external torque, and it will counteract the tendency of the body to want to rotate in the opposite direction to conserve momentum or angular momentum. Now sometimes linear momentum may provide angular momentum. An example of this is, for example, a child that runs and jumps onto a merry-go-round. And this is discussed on page 144 in your textbook. The important thing to note here is that L is your angular momentum, whereas M and V are linear in that equation, and R is your distance to the center of the circle, so that's your angular value. There's also an example on page 144 where there's two rockets on the side of a spacecraft. We can have a look at that one. Once you've done that, go over the questions in activity 9C, questions 1 to 5.